These findings are feeding into models like Dagger, refining our ability to predict space weather in real time. Every flyby, Parker gets closer, faster, and more precise. Its final orbit, set for 2025, will be the most intimate brush with a star any spacecraft has ever attempted. At infinity beyond, we marvel at the irony. To protect Earth, we had to leave it. To shield ourselves from the sun, we had to fly into its fire. The Parker Solar Probe is a message in reverse, a digital bottle hurled into the sun's inferno to return with knowledge that could one day save civilization. In our next segment, we'll explore the concept of solar sirens, how future infrastructure, from power grids to satellite networks, could be outfitted with early warning systems modeled after tornado alarms to respond instantly to solar threats. Because the future of Earth may not be decided by war or politics, but by a warning light blinking from 150 million kilometers away. NASA envisions a future where solar storm sirens may become as common and as crucial as tornado alarms in storm-prone regions. A world where power stations, satellite control centers, and even spaceports can receive real-time alerts and initiate automatic responses within minutes of solar threats being detected. At Infinity Beyond, we believe this vision isn't just ambitious, it's essential. Unlike hurricanes or tsunamis, solar storms don't produce sound, winds, or visible waves. Their most dangerous emissions, X-rays, gamma rays, and charged particles, race toward Earth at incredible speeds, often faster than our current infrastructure can react. That's why scientists are developing AI-based detection models like Dagger, which we introduced earlier, to close that reaction gap. But NASA wants to go further, to install systems that can act autonomously. Imagine this scenario. A satellite in geosynchronous orbit detects a sudden shift in solar wind direction and intensity. That data is instantly analyzed by an AI model trained on millions of prior solar events. Within 1 second, a prediction is generated. Within another second, signals are dispatched globally. Power grids begin isolating vulnerable nodes. Airlines reroute polar flights. Astronauts aboard the ISS retreat to shielded modules. Banking systems pause high-risk transactions. No human intervention required. Just decision-making at the speed of light, because the threat is moving just as fast. This approach mimics severe weather alert systems on Earth. Just like sirens warn towns of incoming tornadoes, solar sirens would act as an early warning system for space weather emergencies. Governments, businesses, and even households could receive push notifications in real time, advising them to prepare, power down, or wait. Such systems are already being tested. In addition to Dagger, other models like Enlil, WSA Enlil plus Cone, and Solar Sentinel are providing simulated storm trajectories and strength forecasts. The European Space Agency, ESA, is working on its own warning network, and Japan, India, and China are also developing domestic space weather forecasting capabilities. But perhaps the most groundbreaking idea is one still on the drawing board: embedding sensors into Earth's infrastructure itself. This vision includes smart power grids equipped with embedded solar flux detectors, deep-sea internet repeaters that can self-regulate when storms are incoming, and even AI-managed aviation systems that adjust altitude or timing to minimize radiation exposure during a storm. At Infinity Beyond, we know this sounds futuristic, but it's already being quietly implemented behind the scenes. Just as meteorology evolved from barometers to Doppler radar, space weather prediction is now evolving into real-time, AI-driven defense. In our next segment, we'll return to Earth's surface, specifically to the vulnerable power grid. We'll explore how a Carrington-level event would cripple not just the lights in our homes, but the entire backbone of the modern economy, plunging civilization into darkness. Because when the sun roars, the only thing between us and silence might be a siren. Transformers, the unsung heroes of our electrical systems, are responsible for regulating and transferring power across vast distances, from massive power plants to your laptop charger. But they also represent one of the most vulnerable links in our technological chain when it comes to solar storms. At Infinity Beyond, we delve into the terrifying possibility that a single solar event could cripple civilization's entire electrical backbone, starting with the very devices that keep the lights on. Here's how it works. During a geomagnetic storm, Earth's magnetic field gets compressed and twisted by the incoming burst of charged particles from a coronal mass ejection, CME. This distortion induces electric currents into conductive materials across the ground, including power lines that stretch for hundreds of kilometers. These currents, called geomagnetically induced currents, GICs, flood into the power grid and accumulate inside transformers. The result? Excessive heat buildup. Magnetic core saturation, insulation breakdown, meltdowns and explosions. Unlike small-scale electrical surges that trip your home's circuit breaker, GICs can overwhelm the core design of massive industrial transformers. When they fail, the damage is catastrophic. And worst of all, these transformers are not easy to replace. Each one can cost millions of dollars, take up to 2 years to manufacture, and often needs to be custom-built for specific infrastructure. And here lies the real danger. There are no global stockpiles of spare transformers. No backups, no immediate replacements. Just a slow, grinding path to recovery. According to a report from the National Academy of Sciences, a Carrington-level solar storm could destroy up to 350 large transformers in the U.S. alone, potentially leaving 130 million people without power for months or even years. Water systems would shut down. Hospitals would rely on limited backup power. Food supply chains would collapse. Emergency services would falter. Chaos would fill the void. In 2012, experts estimated the economic cost of such a disaster in the U.S. at $2.6 trillion, with a 10-year recovery timeline. And that's just one country. Globally, the interconnected nature of power grids means that a large-scale failure in one region could cascade into others, especially across Europe and Asia, where cross-border power sharing is common. A transformer meltdown in Canada, for instance, could cause flickering and blackouts as far as Texas. To counteract this threat, some nations have started to invest in resilient transformer designs, automatic load-shedding systems, and grid-level circuit breakers that can redirect excess current. But progress is uneven. Many developing countries, especially those near the magnetic poles, are ill-prepared. At Infinity Beyond, we believe the time for reactive thinking has passed. We must shift to proactive resilience. In our next segment, we'll examine how a global blackout triggered by solar activity would impact the internet, banking, communications, and even public safety. Because in the 21st century, losing power doesn't just mean darkness. It means disconnecting from the world. Because if the heart of the grid fails, everything else flatlines with it.